Hello friends, welcome to Physics Online. This is continuation of the last exercise we did on electrostatic. We actually did a theory session last time. We looked at Coulomb's law and the vector form. We'll do a few examples or exercises on charges just to superimpose those ideas which we learned there, or rather reinforce those ideas which we did there. Before we begin, a small request from my side, please subscribe to my channel and do comment. That will help me a lot in bringing up the quality of my lectures. Thank you, and let's begin. The first example is a very simple one. It talks about two charges, 2 microcoulomb and 4 microcoulomb. They are placed 25 centimeters apart and we are supposed to calculate the force between them. So we use the Coulomb's law formula, nothing great about it. F is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. The value of 1 by 4 pi epsilon naught, I had told you during the theory session, is going to be 9 into 10 raised to 9, and in all subsequent exercises that we are going to do today, we are going to use this value. The microcoulomb is converted to coulomb by writing it as into 10 raised to minus 6. The distance centimeter is converted to meter by multiplying it by 10 raised to minus 2. Key in the value and you get the answer as 1.152. You can try example on your own by pausing the video. Let's go to the next sum. It's the same looking sum, only thing the wording is different. The charges are minus 3 microcoulomb and 5 microcoulomb. Distance is different, it is 20 centimeter. And they asked you the force on 5 microcoulomb. Now remember a very important point. Whether they ask you the force on 5 microcoulomb or minus 3 microcoulomb, or the mutual force between the two is going to be the same. So we key in the values like we did in the earlier sum and we get the answer as 3.375. And since they have specifically told the magnitude and direction, magnitude is an arithmetic exercise that we have done. Direction, since the two charges are opposite, it will be attractive. So as far as the 5 microcoulomb charge is there, the force will be towards the left. Just a point to mention, the force on the minus 3 microcoulomb will be towards the 5 microcoulomb, that is towards right. Next sum we have three charges. So if you look at the configuration, there are two negative charges, minus 3 coulomb and minus 3 coulomb. We placed a 2 microcoulomb charge, a positive charge, in between the two, so that it's at a distance 15 centimeter from the left charge and 10 centimeter from the charge placed to its right. Here there will be two forces, one due to minus 3 coulomb on the left and minus 3 coulomb on the right. Both of them will be in the opposite direction, will tend to pull the 2 microcoulomb towards each other. So the net will be the subtraction of the two forces. So specified what is F1. F1 is the force on minus 3 coulomb on the left, and the other one is minus 3 coulomb on the right. Of course, the left charge will exert a lesser force because the distance is more. We calculate F1, F2 using the same formula, and as I told you earlier, we simply subtract the two forces. And since the right force is greater, it will be tending to go towards the right. We take up a next thing. Only difference over here is the left side charge has been made 3 microcoulomb, so it will attract, and the minus 3 will also repel it. So the two forces will be in the same direction going towards the left, and they will be added together. Everything else remains the same except that the two forces are in the same direction, so we'll be adding them and it becomes to 7.8 Newton. We go to the next sum here. Now here the things are a little different. We have taken three charges, 3 microcoulomb, minus 2 microcoulomb and 5 microcoulomb. Supposed to find the force on the 5 microcoulomb. The force arising due to the interaction between the 3 microcoulomb and 5 microcoulomb incidentally will be, the force will be towards the right. The distance between them will be 35, and that will be a smaller force. The minus 2 microcoulomb will tend to pull it towards it, it will come towards the left, and the net force on the 5 microcoulomb will be the resultant of the two forces. We will be subtracting the two. So we get it as 2.8 Newton. In case you want to do it, you pause the video, do all the thing. In case you got any doubt, you can send it on the comments to me. Let's go and do another sum. Here it's a different configuration. Here we are looking at three charges, minus through microcoulomb, plus 3 microcoulomb and 1 microcoulomb. They are placed on the vertices of a equilateral triangle of side 25 centimeter. So the angle between them will be 60 degree. That is important when we resolve the forces. They are asking you the force on the 1 microcoulomb charge. Okay, let's see. First we look at the force that the 3 microcoulomb is exerting on the 1 microcoulomb charge. Since both of them are positive, it will be a repulsive force. It will tend to push the 1 microcoulomb charge away from it along the line joining the two charges. As far as the minus 3 microcoulomb charges is, the force between the two will be attractive and it will try to pull the 1 microcoulomb towards it along the line joining the two. As far as their magnitude is concerned, F1, F2 is the same. It is equal to F. Key in the values and it comes out to be 0.32 Newton. We resolve the forces into vertical and horizontal. You will see that the vertical components cancel each other. Primarily they are in the opposite direction and also their magnitude is the same. And the horizontal components add together and it becomes 2F1 cos 60 F1 because F1 and F2 are same. Putting the value, you get the value as 2 into 0.432 into cos 60. Cos 60 happens to be 1 by 2. So the value is 0.432 Newton. Again, pause the video, do your calculations. In case you have any doubts, please comment. Let's go to the next one. We have got 4 charges, 6 microcoulomb, 6 microcoulomb, 6 microcoulomb and 2 microcoulomb. They are placed on the vertices of a square of 15 centimeter as shown in the diagram. Here we will have 3 forces, each along the sides and one along the diagonal. So F1 is due to this one and it trying to push the 2 microcoulomb. F2 is due to this 6 microcoulomb and it again is pushing it in this direction. Both the forces are of same magnitude because all the distance and charges are same and it happens to be 4.2. So they are act in right angles to each other. So their resultant will be F1 square plus F2 square. As regards the third force is concerned, it will act along the line joining the 6 and the 1 microcoulomb. It's along the diagonal. So the net resultant will be like this. Its value, the charges and everything is same except the distance will be 15 root 2. That is a square plus square root of a square plus b square and it's a square, so the diagonal will be root 2 times the side. That comes to be 2.4. You take the resultant of F1, F2 and then add 2.4 to it. You get the value as 9.91 Newton. Repeating again, pause the video, do the calculation on your own. In case you have any difficulty or any doubts, you can comment and I'll get back to you as soon as possible. Okay, let's go to the next. This is a rather simple and common sense question. He's asking you which is the bigger one, a coulomb or an electron. A charge on a electron is 1.6 into 10 raised to minus 19. So obviously it is smaller than 1 coulomb. The next part of the question asks how many charges are there. So it will be Q upon E. So incidentally it will be 6.25 into 10 raised to 18 electrons will make 1 coulomb. In the second question we have a pith ball to which we have given a charge 5 into 10 raised to minus 8 coulomb. Its mass is 8 grams, so it will have a weight equal to 8 into 9.8 acting in the downward direction. We want to keep it stationary in the vertical line, so we need to have a charge placed at B. The question we are answering is what should be the magnitude of the charge and the type of the charge. Obviously the type of the charge should be positive because it needs to repel. Here there are two types of force. One is the gravitational force, that is the weight of the charged particle, and then is the electrostatic force between the two A and B. So we compute both the charges and equate the two. Now if you look at the free body diagram, for the first charge, force is upward, weight is downward. So the F is equal to m1g is the weight of the body, and 1 upon 4 pi epsilon naught q1 q2 upon r square incidentally is the electrostatic force. So equating the two, you get the charge as equal to this, and it has to be positive because it has to repel it. If you have done this, let's go to the next part. This looks really interesting. Basically, you got two charges, plus q and minus q, and they are made, the minus q is rotating about the positive charge in a circle of radius r. He is asking you what is the time period. Before we do the time period, we know any body which is moving in a circular orbit has to have a centripetal force. In this case, the centripetal force is given by the electrostatic force of attraction between the two, that is 1 by 4 pi epsilon naught q1 q2 by r square, and that should be equal to centripetal force, that is mv square by r. So we get the value of v. Now the time period will be equal to distance upon velocity. The distance travelled by the body in one revolution will be 2 pi r divided by v. We substitute the value of v, of course it will be reciprocal of that, it will come in this root like this. Now we take the 2 pi r inside, so when it goes inside it will become 4 pi r square, and we will get the value of t here. I try to make these things very easy as possible for you. You can try all these things again by pausing the video. You can download and do. In case you have any doubts, you can comment and I will definitely come back to you. So we are at the end of the session. Thanks all of you for joining in, and do subscribe to my channel and comment. Thank you and hope to see you soon.